Hello. I'm back for the long long answer, long questions, whatever it's called. I wanted to mention something though. Uh, Someone who's named Sanchai and has a picture of Sanchai, but I don't think they're actually Sanchai. For those that don't know, that is a very famous Muay Thai fighter. So he would not be commenting on math exams on YouTube. But in this short answer question where we did the Maclaurin series, I said like this is a double angle identity, and then I completely forgot the double part. So this should have become a 2x squared. And then what that means is that here was our Maclaurin series for just a regular sine squared x squared. So to do the Maclaurin series of sine squared 2x squared, this is essentially just saying wherever you see an x squared in the original, we're going to include a factor of 2 for every x squared. So for example, this x to the power of 4 has 2x squareds multiplied together. So we would have 2 factors of 2 multiplied. So in other words, this should have a 4. So this should be an 8. And this one is x to the power of 8. So then there are 4 factors of x squared. So we should have 4 factors of 2 as well. And then 2 to the power of 4 is something. I think it's 16. So this needs an extra 16 here. So this is 64. And then, like, I didn't really care, but, you know, 3 factorial has a 2, so you can reduce it. But, yeah, thank you for pointing that out. But we're going to do long answer. Usually, the first question is, like, SL, then maybe first two questions are SL, and then the next 2 are HL. Depends on how many there are. So this looks like a SL function, or an SL question, because it's about, like, pretty basic rational functions. Let's see. We're going to make a sketch, right? We got to include intercepts and asymptotes. So we identify asymptotes first. They do tell you your non-permissible value. This is your vertical asymptote as well. You have a vertical asymptote at 2. Your horizontal asymptote, you will need to compare the degrees of the numerator and denominator. If they're the same, which they are, then the horizontal asymptote is going to be a ratio of the leading coefficients. So there's like a 1 here. So we have a horizontal asymptote at 4. And then for intercepts, the y-intercept we find first because we just substitute x as 0. So then in the top we would have a 2, in the bottom we would have a -2. So we have an x-intercept at -1. Sorry, y-intercept. To find the x-intercept, we are solving for x when y is 0. But for rationals, it boils down to how complicated your numerator is, because this is essentially a fraction. You have 4x plus 2 over x plus 2. This is equal to y. The only way for a fraction to have a value of 0 is if the numerator is 0, like 0 over 2 or 0 over 5. So we don't really need to care about including the denominator in this equation. You would multiply it over to the left side anyways, and it becomes 0. So you might as well just start here and just equate the numerator to 0. So solving for this, you would get -1/2. And then the only caveat or like thing to worry about is that, and I don't even think this is much of a worry because I don't know if this is possible. If this solution is the same as your non-permissible value or your asymptote, then what that means is you don't have an x-intercept. But we do. We have one at -1/2, which is a value that we can have for x. Okay, Then we make our sketch. We have our vertical asymptote here at 2. Our horizontal asymptote here at 4. And then our intercepts, there's one here at -1/2. And -1. And then this is not to scale, but whatever. Okay, and then the rational function shape looks like this. And then over in the opposite corner, for SL at the very least, it will be in this opposite corner over here. And we don't need to have much information about this side. You could take a coordinate like after 2 for x, like 3, and then you can plug it in if you want a definite point, but this is usually good enough. We included everything they asked for. We also want the range of f, so y can be any value except for 4 because we have a horizontal asymptote there. Okay, next, consider this function. So now we have a quadratic, axis of symmetry at 2 roots, so we have 2 x-intercepts. One is at -1/2 and another one at p. And then we need to show that p is 9/2. Okay, easy peasy. So our axis of symmetry is at 2. We have an x-intercept over here at -1/2. And due to the symmetry on the other side, the other root is p. So all we got to do is we got to find out what this distance is right here. And that's just 2 plus 1/2. And then we're going to take that distance and add it to 2. So 2 plus 1/2 is 5/2. And so to get to p, we would do 2 plus 5/2. 2 plus 5/2 is 9/2. Just some quick fraction math. Then we need to find the value of b and c. B and c are the coefficients and constant in here. And then, oh, this is strange. So normally when they have like constants like these, they tell you what type of number they are. So like they told you here p is irrational. So b and c, they don't tell you. So this might throw off some people, but for D, because we know what the 2 roots are, we can write this in factored form. Like this. We also know that the a value is 1, so we'll just leave it like this. And this would throw off an SL student, I think, if this is an SL question, because they're very used to these numbers here being integers. And when you expand this out for your quadratic to have integer coefficients, and they don't tell you that they're integers. So I guess that means that they could be rational. They have to be rational given that we know what our 2 roots are. For an HL person, like you should accept this. This is pretty whatever. But yeah, this would mess up some SL students, I think. Okay, expand this out. And then, oh, this should be 9/2, right? So this is 8/2x minus 9/4. And then for b, well, it's 8/2, so why don't we just say that that's 4? Yeah. So at least b is an integer, but yeah, c is definitely not an integer. Okay. Then we need to find the y-coordinate of the vertex of the graph. Oh, sorry, this is G too. G. Okay, we do know what the x-coordinate is. It's the axis of symmetry, so we're just going to plug in 2. And it doesn't matter which one you plug it into. Let's just plug it into the factored one for fun. You could plug it into this one as well, but they are the same thing. So here is the y-coordinate of your vertex. And then for part F, find the product of the solutions of the equation F equals G. The product of the solutions? Okay. Well, now we're going to have the two graphs intersect. They're going to intersect in a couple of places probably, like at least 2. And this wants the product, so they don't want the actual solutions, which kind of tells me that I don't need to find out what the actual solutions are. But okay, we need to equate the two functions. Ah, okay, I think I see where they're going with this. Nine over 4. Okay, this has solutions. It has probably 3 solutions. What we're going to do is we're going to manipulate this into just a regular looking polynomial. So multiply the x minus 2 over here and expand it out. So we got x cubed minus 4x squared minus 9 over 4x minus 2x squared plus 8x plus 9 over 2. And then have the left side be 0. Collect all our like terms. Oh my god, okay, where are my x squareds? I think I have a minus 6x squared. And then where are my x's? So 4x is gonna minus here. This is 4x. And then 4x is gonna collect with negative 9 over 4x. So these two are gonna collect like terms. So what is 16 minus 9? Okay, well I don't even need to do this, but I'm gonna just do it for the sake of doing it. But 16 minus 9 is 7 over 4. And the most important one is the last one actually, which is 9 over 2 minus 2. 9 over 2 minus 2. Which is 5 over 2, I want to say. Okay, and then the solutions to their intersection would be the solutions to this polynomial. Now, we don't need to know the solutions, we just want the product of the solutions. And there is a formula, or whatever you want to call it, for that. They're called Vieta's formulas. And this thing right here, right, the second coefficient, this is usually related to the sum. But we are more interested in the last one. This one is related to the product of the roots, or solutions, or whatever you want to call them. So as long as I expanded this out and collected it properly, there is a small little thing with this. I forget. There's like a -1 to the power of n or something. Here, let me just Google this real quick. Okay, don't just Google Vieta's formulas because then you would get, you know, oh shoot, this is transparent. Okay, so as you can see here, right, the constant term a0 is -1 to the power of n times the rest of the roots or solutions to our equation. So what that's telling me is that the product is hold on, -1 to the power of 3 times the product of the roots is 5/2. So okay, the product of the roots is -5/2. Yeah, something like that. Tricky. Okay, that took me like 16 marks or 16 minutes. So I'm like mark for a minute. Okay, next up, we have a polynomial. We need to show that x plus 1 is a factor. Okay, we can use our integral or integer root theorem or whatever you want to call it. So if I plug in -1, so in case you forget, x minus a is a root if when you plug in a into the polynomial for x, you would get 0. So it's very easy to check if something's a root. So then we plug in -1, so then we would have -3 plus 5 minus 1 minus 1. And then this equals 0, so this is a root. Then we need to express p, the polynomial, as a product of 3 linear factors. So we know what the first linear factor is. And then what we can do is we can do a polynomial division using this factor to get the quotient, which would be a quadratic, and then you can factor the quadratic. So I'm going to do synthetic division. If you don't know what that is, you can look it up. One -1. This is a 3. 3 times -1 is -3. 5 plus -3 is 2. -2, -1, and then this should be +1, and then that's 0. Okay. So my quotient, if I were to divide by x plus 1, would be 3x squared plus 2x minus 1. And then this is going to be factorable because this is paper 1. So we got 3x, 1, x, and 1. And then we need a plus 2. So this is +1 and this is -1. And then that means that p of x, right, is going to be x plus 1, the first factor they told us, plus these two. Or, well, times these two, not plus. Okay. Then we are going to consider a different polynomial, q, which is these two, and then express 1 over q in this form. Okay, so for c, we're going to do whatever it's called, partial fractions. So 1 over q, and I'll just write what it actually is. It's x plus 1 to x plus 1. We're going to do an equation. It will look like this, as they said. Okay, And then we're going to multiply everything by the lowest common denominator, which is, of course, just the two factors. So this will cancel out here. This will cancel out this one and leave you with a multiplication of 2x plus 1 in the numerator. It'll cancel out this one, and you would have to multiply in an x plus 1 with b. That is going to result in 1 equals, and then we're going to distribute the a in. So this is 2ax plus a plus distributing the b, bx plus b. And then we can solve for a and b because we can compare coefficients. So you see these are my coefficients of x. So I know that 2a plus b, I know that this is going to be 0 because on the left side there are no x's, which means that their coefficients need to be 0 once you added or collected like terms. Likewise, I know that if I just take a and b and I add them together, they should be 1. And then here's a quick system. We're going to subtract off b. And then you'll get a is -1, which means that b has to be 2. And then I guess we need to actually express it and say what this is. So 1 over q of x is going to be -1 over x plus 1 plus 2 over 2x plus 1. Okay, some straightforward partial fractions. Hence or otherwise, we need to show this. Okay. So hence means that we're probably going to use this, the partial fractions. So, okay, let's see what we got. I'm just going to work from here. The only difference is now this has another x plus 1 multiplied in the denominator. So we would, to keep things equivalent, multiply both of these by x plus 1. So this gets multiplied by x plus 1. This gets multiplied by an x plus 1. Okay, so here's that squared with a -1, and then that's this term right here. And then this term becomes 2 terms. Oh, okay. Yeah. And then you're supposed to notice that this right here, right, this is just q again. So they are going to use another partial fraction for q, 1 over q of x, to rewrite this. And what did we say this was? It's this. Yeah, and then we're basically done, right? You distribute the 2 in here, and then that gives you a 4 and then a -2. Yeah. So yeah, distribute this in and then you're basically done. Okay. Hence, now we integrate this thing. So this is the same thing as this, which means that we integrate the partial fraction side. I don't even know what letter this is, but we're going to integrate 4 over 2x plus 1 minus 2 x plus 1 minus 1 x plus 1 squared. There's a dx here. I don't know if there's limits. I don't think there are integration limits. Okay, and then this will be something. Oh my god. I haven't done integrals in a while. Let's see. This is ln, right? I think it is. Let's see. This one would be 2 ln 2x plus 1 minus, and then this one would be plus 1 over x plus 1, and then I guess there's a plus c. Okay, let's see. Gut check, take the derivative. The derivative of ln is like 1 over, right? So that's why this is below. There's a chain rule of 2, which multiplies with this 2 to give you a 4. This is just 2 out here. Derivative of ln x plus 1 is just x plus 1 under. This is basically x plus 1 to the power of negative 1. So then we just use your exponent rules for your integrals, or derivatives. So bring down the negative 1, subtract off 1. Okay, this looks decent. I don't know. You guys can tell me if it's wrong. Then we need to consider this function. So now we're going to take p of x, which is this thing. We're going to divide it by x plus 1 q of x. And then we're going to talk about certain limits here. Okay, so f. So what did we say p of x was? It was like x plus 1. I think it was a 3 minus 1 plus 1. I think that was p, fully factored. And then the denominator was x plus 1 times q. So I know I can just scroll up, but let's see if that's what we have. So here's q, here's p. Yeah, okay, cool. Then what do we want to do? We want to find the limit as x approaches negative 1 and the limit as x approaches infinity. Okay. So x approaches 1. And infinity. Okay, let's see. We can simplify for the first one. X plus 1 cancels with this x plus 1. So your function reduces to this. And then provided, of course, that x is not equal to negative 1, which they said that it wasn't, I'm pretty sure. Yeah. Okay, so what is the limit as x approaches 1? Essentially, we have a removable discontinuity here. So there's just going to be a hole at x1 being 1. And then the function itself will resemble whatever this graph is. So the limit would be what the y value should be at 1 if there wasn't a hole here. I know this isn't what the graph looks like, but like if this is your graph f, you have a removable here, but the limit is essentially what the y value should have been. let's just say that this is the limit. Okay, so then we just plug in 1 into the simplified function. So 3 minus 1 over 2 plus 1. This is 2 over 3. And then if you're trying to find x as it goes to infinity, this is essentially asking what are the y values of the function for large values of x, which is this is essentially asking for a horizontal asymptote. So you can see that it's just 3 over 2, which is the coefficients, right? And then we're done this question. And here's the complex numbers. I haven't seen one in this paper yet, so I was wondering when it would show up. 20 marks. It's been 31 minutes, so I'm on time. 17 plus 16. Okay, this should take me about 20 then. Consider phi. Phi is a plus bi to the power 3. Okay, whatever, phi. In terms of a and b, find the real part of phi or phi, whatever you want to call it, and the imaginary part. So you have to expand this out, right? But of course, you can always use binomial expansion. So I'm going to do that to expand this out. So it's 1 times a to the power 3 plus 3 times a squared times bi plus 3 times a times bi squared plus 1 times bi to the power 3. Okay, and then we'll just clean this up. So this is a to the power 3. This is just 3a squared bi. This one is going to become a minus because of I squared. 3ab squared. And then the I cubed is going to become negative I. So this is negative bi. Which means that the real part is going to be the ones without I. So this one and this one. A cubed minus 3ab squared. The imaginary part would be the ones with I. So this one and this one. So 3a squared b minus b. Huh, they're kind of like, oh, b cubed, right? I forgot to cube my b here. Huh, and then, yeah, okay, that kind of makes sense that they're kind of like symmetric in a way because of the binomial expansion. Hence or otherwise, show that this thing is negative 8. Okay, so all we got to do is we plug in, we know a and b values now. This is a and this is b. We plug them into the real part and the imaginary part, and the real part should become negative 8, and then the imaginary part should become 0, because we know there is no imaginary part when we cube it. Okay, so let's see if that works. Let's do the real part first. So this is just going to be a 1 cubed minus 3 times square root 3 squared. So this is negative 8, so that's looking good. And then we have 3 times 1 squared, whatever, times b, which is square root 3, minus b cubed. B cubed is 3 root 3, so this is equal to 0. So this is good. So as you can see, we don't have an imaginary part when we cube this complex number, and the real part is negative 8. So, done. Okay, we have the roots of the equation. Z cubed negative 8 are u, v, and w. We already know u. They kind of gave us it, right? Yeah. And then v is a real number. And then what? We need to find w, right? You're giving your answers in Cartesian form. Okay, v is the real number because you can keep root -8, traditionally speaking, with real numbers. So v is -2. -2 times -2 times -2. And then w is the conjugate of the complex root. So this is the conjugate root theorem, right? We have a complex polynomial that has real valued coefficients and constants. So if you have a complex root, then the conjugate is also a solution. And then we need to do an Argand diagram. Let me guess, I need to find the area of the freaking triangle that it makes. That's a very traditional question. So here's my Argand diagram. I have one of my solutions is -2. I have another solution here. And then I have the conjugate solution right here, somewhere. And then they want you to find the area of this thing. And then there's lots of ways you can do this. One thing to note though is that u, right, is 1 plus √3i. So this means that this whole length right here is 2 √3. And I'll use a different color. And this here is 1. So we can literally just do a base times height, because these are perpendicular, of course. Base times height divided by 2 to get the area of this. And then I drew this off, not to scale, but these 3 triangles are identical. So once we find the area of this one, we can just multiply by 3. At least I think they're identical. Someone can say that they're not and then tell me how they do it their way, but I'm pretty sure they are. So the area is going to be 3 times the base, which is 2 √3, base times height divided by 2, something like this. So your area is 3 √3, right? And then if you care about units, units squared. Okay, and then let's see. Each of the points u, v, w is rotated counterclockwise or anti-clockwise if you're not from this country, about 0 through an angle of pi/4. And then, okay, these represent new complex numbers. Find these complex numbers giving your answers in this form where theta, okay. So we take each of these coordinates and then we rotate them pi/4, 45 degrees, anti-clockwise. So we can just sketch that real quick. Anti-clock, I'm forgetting which way a clock goes. Okay, so the one that was at -2 is going to rotate anti-clockwise 45 degrees. So it goes here somewhere. And then the rest rotate accordingly. They are nice to you though. For example, you should know that the argument for this and also this is going to be pi/3 due to this is being √3 and this is being 1, so this is a special triangle. So the argument here is pi/3. This one's negative pi/3. But I'm just pointing that out just so that it's easy to kind of visualize where they go after you rotate them. So pi/3 is 60. We rotate it 45 degrees counterclockwise. So that's like that's like 105 degrees. So this one goes here into quadrant 2 a little bit. And then this one goes somewhere over here, like -15 degrees. because negative 60 plus 45. So this is, I forget which one is which. I think this one is V, right? This one's W, and then this one is U. So these are the rotated versions. Okay, you didn't need to do this, but whatever. Because they want the Euler form. So U, V, W. So all of the radii are 2, or magnitudes, or whatever they're called when you talk about complex numbers. Argument is the angle. The length is something. Whatever. Okay, and then we do want specifically your argument to be from pi to negative pi to pi. So when we're talking about how we want to describe the arguments, U is going to be a positive angle, and then W and V should be, we're using negative angles. Okay, U is easy because it's just, it was originally pi over 3, and then we've added pi over 4. So this becomes 7 pi over 12i. For W, we had negative pi over 3, and then we added pi over 4. So this is now negative pi over 12i. And then V is easy because you just rotated it this way, pi over 4, counterclockwise. So this is now negative 3 over 4 pi I. Or wait, no, I have these backwards, right? Oops. Switch these. You know what I mean. Yeah, sure. Okay, what next? Given these are solutions to cube, CDI. Okay, all right. So now we use the Moivre's theorem. And it doesn't matter which one we cube because they're all solutions. I don't know. Let's pick U, this one. So U prime is 2e pi over 12i. And then if we cube it, we're going to use the Moivre's theorem. So this means that 2 will be cubed, and then the argument will be multiplied by 3. Oh, 7 pi. Whoops. Fine. Then never mind. Let's use W and have the negative angle. Actually, no. Let's keep the 7 pi. I don't want to deal with negative angles if I don't want to. If I don't have to. So this becomes 8e, and then 3 and 12 reduce, so this is just going to be 7 pi over 4i. And then we want this in Cartesian form, so this is going to become 8 cosine 7 pi over 4 plus 8 sine 7 pi over 4i. And then you need to know your angles again. This is what? Negative 1 over root 2, and this is positive. Wait, no, this is 7 pi. Oops. They're both negative, right? I think cosine's positive. Okay. 7 pi is fourth quadrant, right? Yeah. Okay, so here is your C and D values. You have 8 over root 2 plus, or minus 8 over root 2. I guess you could rationalize. If you were to rationalize, what the heck would this be? Like 4 root 2? Or 2 root 2? No, 4 root 2, right? Okay. I'll just say that this is good. Then, what is next? Given u, v, w, and their primes are all solutions of z to the power of n for some complex number, n is some natural number, find the smallest positive value of n. Okay. So they all need to be solutions? So eventually, if we keep spinning this thing around, this one and this one, or not spinning, but like multiplying, they'll all end up in the same spot? Okay. 3 marks. Well, okay, if we want the first 3 to be solutions, then we already know that they are solutions to this. So in other words, as long as your exponent is a multiple of 3, u, v, and w will be a solution. So n is a multiple of 3, so I'm going to call it 3 times m instead. So this ensures that u, v, and w this ensures that u, v, and w will always work, right? Now, yeah. Okay, and then that's why we figured this out too. Okay. Now, if we consider these ones, right? The primes. Then what happens is we know what happens when we cube those. That's what this one was right here. And if we were to cube them, you end up with this. Now, if we compare these two, this one is always going to be real valued. In other words, we need to select an m so that this is always going to be real valued. And that's easy. That just means that we need it to be, the argument to be a multiple of pi. In other words, because this is, over 4, then m has to be a multiple of 4. So if m is 4, let's just say m is 4 and see what happens. Then this is going to be negative 8 to the power of 4. And then this one here is going to be 8 to the power of 4. And then e 7 pi I. And then 7 pi is... Hold on. 0, 1, 2, 3, 4, 5, 7. 7 is... Okay, so 7 is here, right? So this would be a negative number, whereas this is a positive number. So 4 is not enough. That means that m has to be 8 then, the next multiple of 4. So if m is 8, then this would become an even multiple of pi. So then this would end up being positive, and then this is always going to be positive because m has to be a multiple of 4. Yeah, so 4 is not enough because this would end up being negative. M has to be 8, which means that n, the smallest number for n is what, 24? That sounds pretty good to me. 3 marks? Sure. Okay, and then we're done. And yeah, 50 minutes. So just in time, 1 minute per mark, which is what IB recommends. Of course, I was talking and kind of explaining things. All right, I hope that this was relatively error-free, but like I said, let me know if there are any errors. It's not like I have the answer key or the mark scheme. I'm just kind of doing this. And okay, oh yeah, and let me give my thoughts for this exam, including the short answer. I think this is not a hard exam, but there are certain questions that I think would be considered hard. For example, I think this one is very untraditional. Like I don't think you would find a lot of questions from former exams or the question bank that would be like this. I think it's a fun question though. This one as well is a little bit tough. I messed up on this right here, but it is a pretty standard Maclaurin series question up until this last one. The induction was pretty standard. Volume of revolution was standard. Oh yeah, this geometric series one. I think this one was kind of, again, very interesting, but maybe in a test situation, this would have been a little bit hard to do. And then I think the rest weren't that great. They were like your standard SL questions, so pretty easy and definitely questions that you could have seen in question banks or practices. In terms of the long answer questions, this is very standard. This last one is a very HL only thing, so I wonder if this was included in the SL question. The rest of it is very SL, but this last one where you had to use Vieta's formula, that's an HL only thing. But overall, this is a very standard, like, rational question. This one's standard. There's nothing crazy about this one except for maybe this hence or otherwise one right here. And then the last one is okay. I think this one is pretty challenging. Not super challenging, but does test your knowledge of, complex numbers. Overall, yeah. I think if you get the stuff, then this exam isn't that difficult. It's like, but if you don't get your stuff, then it would be harder than maybe a usual one where it's like very flowchart and these questions already existed and you just follow the steps that are already laid out for you. Because I feel like this one you need to do some of your own thinking because you need to apply your understanding, which, isn't a bad thing in an exam. That's ideally what a good exam would be, at least challenging questions. And those would be the questions that separate the 6s from the 7s. But yeah, I wouldn't say it's hard, but it is, you do have to know your stuff. Okay, thank you for watching. I don't know when paper 2 will be. I honestly hate paper 2s the most because it's just like calculator work. They can give you like the most crazy, ugly ass question and then you gotta solve it. And it's very easy to solve because you just put it into the equation solver, but like there's no elegance to it like these questions in paper 1. So maybe I'll do paper 3 first because paper 3, even though it is calculator allowed, it generally has a bit more elegance to it because you're following like you're examining some sort of like either pre-existing theorem that they don't tell you is a theorem or something interesting. Okay, that's enough of me yapping. See you all later.